today I want to explain the final projects. So final project is similar to the one in STAT 5030 or STAT 6840, but maybe some of you have not taken my applied statistics courses before, so I would like to explain it. And yeah, then we go to chapter 7 lab for the generalized additive models. And on Wednesday that we will decide the final project dates. So I think that we have 13 students, so that means that we have, I think, the 3 days we need for presentation. So we have 75 minutes lecture. So I think that we have at most 5 presentations per day. So probably we will schedule maybe 4 presentations for the first 2 days, and then 1 presentation on the last day. So yes, so I think the syllabus lists the presentation dates, so I will share the screen. Okay, so this is the syllabus. Yep. So presentation dates are April 19th and the 24th and the May 1st. So just check your schedule by the next lecture so that we can decide. So I think we have 13 students, or maybe 4 students for 19th, another 4 students for 24th, and the other 5 students for May 1st. And just make sure that you are available on the last final presentation dates, the 6:30 to 8:45. So this is online class, so you will make online presentation. So you can share the screen and you can make a presentation. And the final project plan is due on March 31st. So that is, I think, 11 days from now. So I think it's a good time to start. But if you start too early, then you haven't studied many models. So that's why I haven't discussed it until today. Okay. And I have graded midterm, and the grading this midterm is hard. So I printed out everything and I graded, but I found that this is an online class, so I cannot really return it. So I think probably I will scan it and send it to you. And overall, you did pretty well. I think probably it's best in the past. I think the students' ability in data science is increasing over time, especially for question 1 and 2. I think question 1, I think majority of students get maybe 90% or more. Question 2, maybe slightly less, but in question 3 also many students get close to the full credits. Maybe, and I think that yeah, and also I checked the performance of your model, and James is here. No. Oh yeah, James got the best prediction performance for the last question. So the AUC, the 5-fold cross-validated AUC of 0.767, and other students I think many students got close to 0.76, maybe 0.759 or something. And I made a sample solution. I will not share it, but share with you, but I will just show it. I will show the preview. And remember that we are regressing some default status by the credit card payment information and the demographic information. And yeah, to be short, my score is 0.781, about 0.781. So still better than all students. And this is the model I used, I think. So I used some polynomial of the payment information and also interaction term between sex and marriage or education. And also I take the, I think the log scale variable for payment information, because large amount does not linearly affect the default status. And also I put some interaction between the balance and the payment information. And I optimize this in terms of AIC, and AIC isn't really most reliable predictor. So if you do very computer intensive cross validation for model selection, then probably you can do it better. But with this, AIC is 25,774. That is, I think, much smaller than AIC for the baseline model in question A. In question A, actually AIC is 27,459 for the 7th degree polynomial. So 27159 to 25774. So it's pretty small. Yeah, but I think that this time the yeah, overall you did pretty well. I think last year only a few students can get the correct result for the last question. So either cross validation is not correct or model building wasn't correct. Okay, that's it. So the James will get some bonus credits. And the second one is, I think the yeah, second one is actually Colin. Colin here, no. But the Colin's the oh yeah, the cross-validated AUC isn't 100% correct. So it does not the boost your score, but the cross validation is not done perfectly. But the score is the second 0.766. So it's close to the James's score. And for valid score, valid the cross validated AUC, the second one is Nathan, but that is 0.76 or something. So it's close to other students. Yeah. And that's it. Okay, so now I will share the screen and so first, for final presentation, I would like you to sorry. So I would like you to submit a project plan. So project plan is just 1 to 2 page summary of your project plan. So data and analysis plan, and due on Friday, March 31st. I will open the submission form online and attach additional pages for data sample. So this is important. Also, I will prepare the submission form for CSV and Excel. And the plan will be graded and you will receive instructor's comments. So until last semester, I didn't give any points for the plan, but that makes some students feel it's not important. So this time I will give 3% of course credits to this final project plan. And you may be asked to submit a plan again if it is not developed well. So that means it's important to submit the meaningful and the well-developed plan. So if not, then basically you have to submit it again. So, yep. And
how early would you want the project plan? in case, for review, because
you can just submit by the March 31st, and then I start grading. So yeah.
deal.
And you can, of course, talk to me in office hours to discuss your final project. But yeah, usually I don't review before this submission date. Yeah, so you can talk to me, but for submission, you can submit by just Friday, March 31st. Yeah. Yeah, so some students, they worry too much, and they sent me this project plan maybe twice or three times before submission date. But that is good. But if all students do that, then I don't have enough time to review all materials. So yeah, if you have concerns, then you can talk to me in office hours, or maybe some short emails are also fine. Yeah, and set a meaningful. Okay, so some tips for to make a good final project plan. So set a meaningful objective in the real world. So often, sometimes even if the data set is good, sometimes some students do trivial analysis. For example, regressing left lung volume on right lung volume. Then probably you can see if the left lung volume is Y and the right lung volume is X, then probably we can imagine that Y is almost X, right? So maybe 0.01 plus maybe 0.99X plus epsilon with very small error. But this isn't really, interesting. So usually we have some relationship. We expect some relationship between X and Y, and we hope that the X is a useful, the predictor for Y, or useful factor to explain Y. So set a meaningful objective in a real world is important. And collect or make a feasible plan. Sorry, I think this is a little bit. Yeah, sorry, they make a feasible plan to collect data. So if too many predictors, too many observations, and also combining too many databases, data sources, and also if you have to, gather data by yourself, then it takes time. Some students did some survey, their own survey, maybe online survey, to get some data, then analyze it. But that is a little harder for this class. 50-30 only discusses linear regression. So maybe some simple survey data works good. But for this course, it's slightly more difficult. But still, some students did that. But yeah. And and also consider how clean the data are, because you have only limited time. So if data isn't clean, then you have to be careful that it takes time to clean the data. Yeah, so yeah, missing values are most important ones, maybe. Then duplicated data points and the recording errors. And a data set with independent observations is ideal. I think this is an important point. So typically, if you get the time series data, then it's probably hard to analyze it. For example, suppose that you want to explain the number of COVID deaths by the temperature, maybe overall average temperature in the United States or something, then you have 1 year of data. Then temperature depends on season, but you only have 1 year of data, and observations are dependent. Today's temperature and tomorrow's temperatures are closer. Today's temperature and temperature on July 1st are much different, right? So we have dependent data and seasonality, but we only have 1 year of data. So that is hard to analyze. So it's not impossible, but you have to be careful about the dependent data. And I think that this course, if you're taking this course, probably you don't have much trouble. But some students try to analyze summarized data, and that is a big mistake, right? So suppose that we have originally 5,000 observations, maybe 1,000 patients of some disease, and 4,000 maybe benign people. And you have the mean weight and the mean height and the mean blood pressure or something like that. But if you only have summarized data, then you cannot analyze it, even if original data has 5,000 observations. So you need original data set. So raw data, and you have the data for sample units. Yeah. Yeah, and also you have to consider the statistical models which are appropriate for your research questions. Typically, this course deal with the regression or classification, maybe some unsupervised learning. Yeah, and just to make sure that you understand what is response and what are the predictors. Yeah. And I also provide a sample project plan, but you don't really have to stick with it. So just make your own project plan. So sample is just one sample. And finally, the evaluation on final project, the quality of research question, originality of data collection, and the quality of data analysis and the presentation, and the votes by classmates. So you can use, yeah, I think that I have to also mention that if you use the data competition, so the data for the data competition, for example, Kaggle competition, then you cannot set the same objective as the competition, because the Kaggle competition has many, sample codes and the sample results. So you can use the data if you are interested in that data, but you have to set up your own objective. And originality of data collection and the quality of research question are important. So you can use any data, but if you want to get the top score in the presentation, then I recommend you to gather the first source data, not ready-made data. Yeah. Do you have any questions so far? I think that many of you have made a presentation in my applied statistics course. At least I think the Hunter and I think James and Victoria Thomas. Colin also made a presentation, right? Yeah, and Erica, of course, and Ryan. Maybe this is the first time to take my applied stat course, maybe, but yeah. Yeah, I will upload maybe 1 or 2 sample presentation file later, but yes, and yeah, Bill also haven't taken my applied stat course, but I think that you have taken Stat 5030 with Professor Kohn.
Yes.
Yeah. And this is my sample project plan. This is not a real project. Actually, I made up a sample project plan based on one student's project in the past. So for example, character recognition by 16 variables. So objectives are the character recognition. So the objective of study is to compare the forecasting performance of different classification models, such as logistic regression, KNN, and the support vector machine for character recognition. So character recognition, we have 26 characters. So basically, we have 26 categories in the response variable. And this is a good machine learning topic, pretty popular one. And this character recognition isn't really based on the image of handwritten characters, but this is actually the summarized data set. So we have, okay, so each sample unit is a letter. Actually, this is a letter in different fonts, not really the handwritten characters. But the original image is, I think, the 20, sorry, I'm not exactly sure, maybe some resolution we have, maybe 24 by 24, maybe 16, and maybe 16 by 16 pixel data. So originally we have 256 cells, but the it has just 16 summarized variables, such as, you know, the average, the place of the dot. Okay, so suppose that we have the white and black pixels, the 16 by 16 pixels, and the 16 variables are summarized variables of those 16 by 16 pixels. Maybe the average height of the black dots, or average, you know, the location, the horizontal location of the black dots, or the number of black dots, or something like that. So just 16 summarized information. And based on those information, that we can do prediction. So yeah, so at first describe the data. This data is actually from the UCI machine learning repository, so it's simple. Then you can describe the sample size and how many variables are there, and how the data looks like. And also you are supposed to attach the sample data or the entire data set. And yeah, and you can describe the methodologies that you are planning to use. And maybe you can describe how to summarize results. And this is not mandatory, but if you think the plan is too difficult or maybe too challenging, then you can set up our backup plans. And anyway, you can change the plan when you are analyzing data, but you can plan if you have backup plans or challenging plans. These are not mandatory, so these are optional, but you can just brainstorm the project. Okay, so and then you can attach the data. So this is the description of 16 variables of the characters, character images. And also this is the sample data. So these are the answer, so label, response variable, and these are predictor variables. Yeah, so in this case, I attached the sample data set, but you can also attach the entire data set by CSV or Excel. If you have not collected data at the time of submission, at least you can submit a kind of the dummy data with correct, predictor labels, and also some dummy data showing how data will look like. Do you have any questions? Yeah, I think it's pretty similar to other applied statistics course projects. This is data science course, so maybe you can heavily use cross-validation. That is one thing. And also you can compare multiple methods. Then, that project is at a higher level. So if you do just one analysis by LDA, and it's done, that's fine. You can pass the course, but if you compare multiple methods to see which one performs better, then that project is more advanced. Yeah, okay. Yeah, if you have questions, just let me know at any time. And now that we discussed chapter 7.7 and the lab for 7.7. I think we actually discussed this last time, but it's more than a week ago. So just I quickly review the GAM, generalized additive models. Then we do lab session. Then if we have time, then we go to chapter 8. And hopefully next time that we will also have exercise for chapter 8. Okay, so the generalized additive models. So this is different from earlier sections of chapter 7 because we are assuming there are multiple predictors, x1 to xp. So this situation is much more complicated because in general, the prediction model is y is equal to f of x1 to xp plus epsilon. So that means we can include x1, x2 or square root of x1, x2. So we have the interaction terms. So we have a more complicated setting. But that is usually too complicated. So one simple way is we assume that the yi is linear combination of just the fj of xij. So here, the j is the index for predictors and I is the index for observations. So just this assume that the effect of x1 to xp on y are just not related to each other. So basically, we have to specify how f1 or f2 or f3, fp these look like, but except for that, we don't really have to specify a relationship between, more complicated relationship between y and x1 to xp. And here is an example. So this illustrates the regression results when wage is regressed on year and age and education. So this is a kind of marginal relationship between year and the wage. So you can see the year 2009, basically the later year that we have a slightly larger wage. And the age and the wage, it's more complicated relationship as we discussed before. So age 35 to 60 are higher. Wage for the age 35 to 60 are higher than younger or older ages. And effect of education. So education is categorical variables from high school dropouts to maybe the attended graduate school. So we have some nonlinear effect, but this is a factor variable. So basically we do ANOVA on this. So ANOVA for wage on educational level. And if we combine this, so we can at least do slightly better than usual multiple linear regression. And this is by list square. So this is by regression spline, and you can do this with the smoothing splines as well. So remember that regression spline is basically we are fitting piecewise cubic function. So we have a little more parameters for predictors because we have the not points, and after not points, then basically coefficient changes. So we have the more coefficients than usual polynomial regression, but basically it's the same as regression. Smoothing spline is more kind of the quantitative approach. So we optimize the shape of the curve based on the smoothness parameter. So yes. And the GAM can be used for the classification as well. So this is the logistic regression case. So the right-hand side can be the summation of function of x1 to function of xp. Okay, and then we discuss generalized additive models here. And the package is the GAM, so generalized additive model. ISLR package is for the data. And I just want to discuss some data visualization. So I load some library, the correlation plot library, CORL plot library, and the performance analytics library for correlation plot and the chart.correlation. And this is the usual, the pairwise scatter plot, but this isn't really very good because the some variables are categorical. And also relationship is not clear, maybe partly because there are too many observations. So correlation plot is here. So you can see the 4 variables here. So if we put 4 variables, you can make a 4x4 correlation plot. So you can visualize it in this way. And this is the scale for correlation. And obviously, wage and wage has correlation of 1. And the same variable, always correlation is 1. So these are trivial parts. And the other part, you can see the wage and the education are highly correlated. So the correlation of maybe 0.5. This is just by color, so it's not exactly clear, but it looks about 0.5. And this and this have the same information. So actually, this is redundant. Only essential information are the 6 pieces of information. And age and wage are somewhat related. So that's also true. But the relationship is more complicated. So correlation does not capture the entire relationship between this. Year and wage are not correlated much. Maybe partly because this is in recession and wage is almost flat. And another one, the similar one, but the chart.correlation in performance analytic package, you can just put the 4 variables here, and then you can get slightly more, slightly fancier graphs here. And these are, you can see, these are scatter plots and also some trend line. And you can see correlation here, 0.2, 0.48, 0.038, 0.071, and also significance. The correlation have correlation test. So we have correlation test. So 3 dot, I'm not exactly sure, but this is probably somewhat significant. I don't know, p-value of 0.01 or less. You can check the specification, but that is a significant correlation. 0.014 isn't significant correlation. And actually, you can see that the year and the wage have also significant relationship, even though correlation is not very large. So sample size is large. So yeah, and okay, so now that we go to the GAM, the generalized additive models, and actually you can fit just as a linear model, so it does not require any package as long as I'm not sure if this natural spline function is in which package, but you can just fit GAM as linear model. So this is natural spline, the regression spline, with orthogonal basis. So you can put this, then you can fit the graph. You can fit the model. And yeah, so this is just another one with the GAM function. So basically the GAM is linear model if we use the spline, the regression spline or polynomial regression. So you can do this. And this the GAM of this summary. So you can see an over table for each variable. You can see the year is the regression. So this one. So this one is the regression spline with degree 2. So the degrees of freedom is 2. And you can see the p-values. So this is ANOVA table. So this is the sequential ANOVA table. So you can see the year is significant predictor, and given that year is included, the age is also significant and the education is also significant. And still the residual size is large. You can see the sum of the squares explained by these predictors, maybe in total about 150, sorry, the 1.5 million, but the residual is 3.7 million. So maybe we have only explained maybe 30% of the entire variation by this year, age, and education. But yeah, so you can see this. Yeah, so the education is really the largest factor, and age maybe explain half of that amount, additional amount, and the year only explains the 20,000 of the variation. And also we can use the smoothing spline. So this looks more complicated. At first, smoothing spline is not a regression, but okay, so still we can use this GAM function to fit. And the complicated part is the analysis of variance part. I'm not exactly sure that what is the procedure for this. So at first, this is not linear regression, so we cannot do usual f-test. Right? So these are, I think, somewhat the approximation method. And these are outputs at first test if these variables are useful as just a linear factor. So what if we include a linear term of year? What if we include just the linear term of age? Then degrees of freedom is 1, and we can see how significant these variables are. Then after that, it tests additional terms. I'm not exactly sure about the procedure, but also that it lists the output, which explains whether or not this is useful. So you can see that, for example, the year variable, you can see the linear term is significant with very small p-value, but the additional term isn't significant. So that means that we used the 2 degrees of freedom for year, but the 1 is sufficient probably. And age is actually pretty significant for 2 additional parameters. So basically, roughly speaking, the cubic curve is useful to fit the cubic curve of age is useful to predict the wage of people. So this is the smoothing spline, so not exactly cubic curve, but the curve which has the same effective degrees of freedom as cubic curve. So that is useful. So probably based on this result, that you wanna use the linear term of the year variable and the smoothing spline of age, and also just include this factor variable education. Then you can explain wage somewhat well. And this is the also the, I think this is the probably this is the confidence band for the the 3 curves. So the spline for year and the spline for age, and just the factor variable of education to explain wage. Yeah. Yeah, so this is the GAM1S and GAM2S. So GAM1S is actually slightly smaller model with only the effective degrees of freedom for year is 1, and the GAM2 is 2. So GAM1, the graph is this, and GAM2 graph is this. So we allow a larger effective degrees of freedom. So we have some curvature, but this is not statistically significant. So this one is probably sufficient to explain the situation. Do you have any questions? So in short, GAM is almost the same as multiple linear regression, but if you use smoothing spline, maybe algorithm is more complicated. So you may want to use the GAM function, and it also returns some more complicated test results. Yeah, so that's chapter 7. Okay, so what time? 7:13. And the next topic is tree-based methods. So have you ever studied the tree-based methods or random forests? Not yet. Yeah, I guess maybe some of you have experience if you do some Kaggle competition or something. So the tree-based methods are pretty intuitive originally. Tree-based methods is a framework for regression and classification by simple partitioning of variables. So this is the log of baseball salary data analysis. Baseball players, I mean, professional baseball players' salary data. So this is response. Okay. And the predictors are the years they played. And the next one is the number of hits in the previous season. So if you play longer in MLB, then your salary is going up. But of course, it is based on performance. So if you make more hits, then yeah, so the salary gets higher. Then one intuitive way is we consider some condition. If year is less than 4.5 years, then anyway, their salary is low. If more than 4.5 years, the number of hits is larger, salary is higher. But number of hits are smaller, the still salary is slightly higher than younger players. So this is the basic idea of tree-based methods. So this is pretty intuitive. So people's decision is usually binary, right? Even within your brain. So each decision is made binary. So your decision is digital, maybe the sequence of digital decisions. Yeah. I think one reason that you study statistics is the people's decision is binary, and it's hard to deal with the more complicated quantities. People cannot distinguish baseball player with batting average of 0.275 and 0.270. But if you use numbers, then you can certainly distinguish it. Yeah, and the regression tree basically use this idea. So regression tree splits the predictor space with a single predictor at each step and fit a regression, typically just a constant. So in this case, we split the data, baseball players with years of experience less than 4.5 years. Just we take average, right? We can fit some regression model still, right? So still within 4.5 years, then still if years of experience is more, then maybe salary is higher. Maybe experience of 4 years, player with experience of 4 years has higher salary than players with experience of 3 years. But we just fit the constant here. Also, the number of hits may matter even if the years of experience is shorter, but we didn't consider it. So just typically a constant in each region. And yes. And this split is made so that the error is minimized. So you can think about the fitting the one value, maybe A, and the one value B, and what is the best, separation. So we minimize the error size to decide at which point we divide this data set. Yeah, and then after that we split this again. So you can maybe split this right-hand region, maybe around here, or maybe left-hand region around here, and we just split the region to minimize the sum of squared errors. So in this case, just we made 2 splits, then we stop. So this is the case. And yeah, you can see why we don't fit the complicated model. For example, even for each region, we can fit the linear model. For example, y is equal to beta naught plus beta 1 times number of hits, and the beta 2 times number of years. But in such a case, probably these function is not continuous on the entire space, right? So that we determine this regression model for this region and this region and this region independently. So we have some contradiction on the boundary between R1, R2, and R3. So that's why probably people don't really care too much about it, and we fit just a constant. So this is the image of fitted value of regression tree. So in this case, yeah, we have several splits. How many splits here? We split here, right? And we split, maybe I should say that. Splits by making lines. So one split here, and another split here, and another one here, and another one here, I think. So we have 4 splits, probably. And we have different average values. So you can see that this can deal with pretty, complicated pattern of, yeah, it can express pretty complicated function of x1 and x2. Yeah, then next problem is, okay, so in this figure, we make the 4 splits, and the previous example, we made 2 splits. And if we split more and more, the training error gets smaller, but the test error may not become smaller. Of course, if we have 100 observations and we make 99 splits, then every observation have each region, and the training fit is 100% correct. So the error becomes 0, but that is usually overfitting. So how to optimize the complexity of tree? So that is the next topic, and how to determine the size of tree. So the number of splits T in regression tree is determined so as to balance the size of tree and the total error size. So as model becomes more complicated, the error size gets smaller, but the size of T gets larger. So T is the number of splits. So if previous figure 4. And we basically penalize the size of T. So this is similar idea to AIC or similar idea to lasso. So we penalize the complexity. Then if we use appropriate alpha, then the fit should be good. So to be exact, for each value of alpha, alpha is a positive number, they minimize the objective function above to determine the optimal subtree. So subtree is obtained by removing some of the splits in the original tree. Yeah, so at first we make a large tree. Possibly, if we have 100 observations, you can have a tree with 99 splits. Then after that, we just eliminate the sum splits. Then we can make a smaller tree. Then we can do we can use that's the so-called pruned tree as our final model. And alpha is a hyperparameter, so it is usually determined by cross-validation. So the tree size T is discrete. So if 100 observations and we make the largest tree, then still capital T, this size is either 1, 2, 3, maybe up to maybe 0 is possible, but the 0 to 99, right? So basically the alpha value corresponds to the size of tree. So alpha gets larger, then obtained the tree size gets smaller. So we have the basically yeah. So at most we should consider n different values of alpha, and based on those models that we can choose the best alpha. So based on the cross-validated error, that we can choose the best alpha. Yeah. So the tree algorithm is, at first, they make a large tree. Then for each value of alpha, they prune the original tree to minimize the cost function in the slide number 5, the previous slide. And they use cross-validation to find the optimal alpha. So that is the procedure to get the tree. And that is for regression, but the classification trees is also possible. So the tree methods are applied for classification. And so this is almost the same way as the regression. In regression, we minimize the sum of squared errors. In classification, we minimize basically the error size, but so one is error rate. And another way is the more likelihood method. So that we calculate the -2 times the log of maximum likelihood, and that we minimize this quantity. And this is described by this. Yeah, maybe to be exact, suppose that the terminal node I has ni observations. So when we make a tree, we impose some assumptions. For example, if sample size is too large, then we assume that each node will have at least 100 observations or something. Then we stop at this point. And suppose that the node I, terminal node I, that is the specific region, has ni observations, and of which the lowercase ni observations have label 1 and the others have label 0, then we can count the number of successful observations, label 1 observations. So that is pi. Then we can define pi as ni over capital Ni. Then that means the ni is pi times ni, right? So this is ni, lowercase ni, and this is the capital Ni minus ni. Then you can see that this is log likelihood function of that node. Okay. So we have ni observations categorized as 1, right? So that likelihood is pi to the power ni. Pi is the probability to be 1. So, and the likelihood for the other ni minus ni observations. So this is label 1 observation, and this is label 0 observations. And we have capital Ni minus lowercase ni observations with label 0. And that likelihood is 1 minus pi to the power capital Ni minus ni. So if we take logarithm, then that becomes this. So you can see this summation is the likelihood for, yeah, so the likelihood for this the data set. So you can minimize this -2 times likelihood. Yeah, so classification tree can be done in a similar way to regression tree. So do you have any questions so far? Which is better? What do you think? Error rate and the deviance. What are the difference, practical differences? If you analyze data, which one do you use? Suppose that you only have 500, maybe 300 observations for binary classification problems. Do you use deviance or error rate? Suppose that no outliers. Probably if
Error
the no
rate,
out,
though.
yeah, go ahead.
I'm trying to think about how it would work. I know the difference. We definitely know the difference. I'm just trying to think about if it's more volume related as to which one I would choose.
Yeah.
I'm not sure yet. Thank you.
Yeah. So suppose that we only have 300 observations, then probably I would go with deviance, because error rate has less information, right? So error rate is just like maybe 15 out of 300 are incorrect or something. So that is a pretty small amount of information. Only possible values are, the 0. I mean, only possible values are 0/300 to 300 over 300, right? And if the model is good, then usually this is small. So just we are thinking about 0/300 or 1/300 or 2/300. Maybe if we have two similar regression trees, maybe they have the same performance. So probably I would go with deviance. But if we have some outliers, then sometimes one observation destroy the entire likelihood function, right? Because the one extreme observation makes very small likelihood, and that broke this likelihood function entirely. So the deviance is fragile against outliers. So in such a case, maybe I would go for error rate. So maybe larger data set, maybe error rate, maybe appropriate. Yeah, binary classification problem. If sample size is not huge, usually we have estimation problem. We can estimate it, but the result isn't very reliable. Okay, so the next one, the linear model versus tree-based methods. Which is better? And the answer is it depends. And this is the true boundary for data. So okay, so this is the true 1, and this is true 0. Green area is true 1, and the yellow area is true 0. Okay, so this is the data set 1, and this is data set 2. Yes, I think. Sorry. No. So truth should be the same for the same data set. So this is the true 1 and the true 0. So this is data 1, and this is for data 2. This is the by linear logistic regression. Linear logistic is a logistic regression with linear term only. So by linear model, I would say maybe I should say just the logistic regression with only linear term. And this is the tree-based method. So if truth is like this, then boundary is just a straight line. So this is identified by logistic regression consistently. So this is basically, in this case, logistic regression win. And if we use the tree-based method for this data, probably at first they divide the data set by this boundary, then maybe this boundary and this boundary and this boundary and this boundary. But still, the error size is pretty large. So probably, so this region, and this region, and this region. So these three regions are classified as 0, but we have some errors, right? So we have errors here, and errors here, errors here, and errors here. So we have some errors here again, also here. So basically this one is the left-hand side is better. But for data set 2, the true one has this shape. The region for true one is this area, and the true 0 is here, and the true 1 and the true 0. And this area is correctly specified by tree-based methods. Right? So just the first this boundary and this boundary, then this is classified as 0, and the other two parts are classified as 1. So basically, this one win. And this one, if we use the straight line, actually we have error here, and error here, and error here. So in this case, the tree-based method works better. So it really depends on the situation. Yeah. Probably the truth is the in-between, the data 1 and the data 2. So probably not linear boundary, but also not this kind of, boundary. So yeah, then which one is better? It really depends on the case. And tree-based method is more flexible. So finally, usually it performs better. And the neural network is, oh, sorry, go ahead.
I'm just trying to think about it, because best case in data 1, best case in data 2 depends on in the modeling. But if you do, the assumption, if we get data, would be once we see some of the samples, we might know which one is better or worse. One is, tree structure allows for square corners, and logistic or linear would give you straight lines. Those are two completely different data sets. So I'm kind of, the question that comes in to me is, do you have a rough idea ahead of time on how these would do, or is in the real world, and do you fall into place for tree structure? Seems very coarse to me.
Actually, not really. So the linear model cannot get very complicated. You can think about polynomial regression or something, but it isn't clear if those higher order terms effectively explain the more complicated situation. So I think the short answer is, if the truth is complicated, then tree-based methods are better. Truth is simple, then probably the linear regression, logistic regression work better. Yeah. So I think that is a short answer. And yes, of course, if you include some terms more carefully in a linear regression, it can perform better. For example, suppose that y and x1, x2 are complicated, have the complicated relationship, and y is equal to suppose beta naught plus beta 1x1 plus x2 beta to x2 plus epsilon. So this does not work well, but the tree-based method works well. If you modify this linear model into, for example, beta naught plus beta 1x1 plus beta 2x2 plus beta 3x1 square plus beta 4 square root of x1 x2 or something, then maybe it works excellently, but sometimes it works very poorly. So it is really difficult to choose this kind of engineered variables. So if your choice is very good, then maybe the linear model with the complicated predictors may work. But if you don't have any prior knowledge, then tree-based methods may work for any situation, any complicated situation. Yeah. And the neural network, maybe we will cover it later. Neural network is a kind of similar to tree-based method because the both models have the philosophy that we don't know the truth, but we automatically fit the complicated patterns. But the neural network isn't this kind of digital boundaries. So it's more flexibly fit the model. So if truth is complicated, smooth surface or something, then neural network usually works slightly better than tree-based methods. But yeah, those are maybe some characteristics of these models. Yeah, and advantages of these tree-based methods are, at first, the results are intuitive and displayed graphically. So we split, the baseball players by years of experience, then the number of hits. So this is maybe for most people, it's easy to consider. And the no need to create dummy variables for categorical predictors. So I think this is not really advantages, maybe. Anyway, when we make a split, you have to consider how to split the variable. So yeah, so this is a little questionable, but if there is a good built-in algorithm to split the categorical predictors into two groups, then it works great. And disadvantages, the predictive performance is generally not high. So this is still a very, very basic idea, and we need some improvement. And the naive tree regression does not work very well in most cases. And second one, the not robust, a small change in data dramatically changes the results. You can see that suppose we think about a binary classification problem. We have 4 observations here. 10 observations here and 3 observations here. Then probably the best split point is here, right? This is basically 0/4 or something. This is maybe 10/13, and this is the best split. But if we don't have this observation, but we have 1 observation here, then I think split is here. So it dramatically changes. So it's not very good. So it's not very stable model. So not robust. And another thing, the methods often suffer from overfitting. Yeah, of course, if we have 100 observations and we split this 50 times, then usually it's overfit. So yeah, So this is pretty ad hoc method. So just the, split the data into two based on the, training performance. So it can easily overfit the situation. And the methods to improve trees, and we have 3 methods here in the textbook. It is well known that tree-based methods have a high variance, so it's not stable. You can imagine that the split is largely determined by chance, so it is unstable. Basically, decision is 0, 1, so that is usually unstable. Right? So, and the following methods improve the performance of tree-based methods. So one is bugging. So basically, we develop trees multiple times, then take average. Then, you can see the surface is smoother. Still maybe digital, but you can see the first, the split is like this, and the second split is like this. Sorry, this is almost the same. So second split is like this, and the third split is like this. And in total, how does this look like? Then probably if we take average like this, right? So it becomes smoother. So this is bugging. And the random forests, this is a little counterintuitive. They're similar to bugging, but each randomized sample contains, sorry, the I is redundant, contains the fewer randomly chosen predictors. So we fit Y on X1, X2, X3, X4. In bugging, we randomize the training set to make a tree. So suppose, for example, we have 100 observations. We maybe randomly take 100 observations with replacement. Then we get a tree, and we repeat it 100 times. Then take average. Then that is the bugging. But the random forest, Y on X1, X2, X3, X4, but we also sample these predictors. So set 1, maybe the randomized set D1, that we only fit Y on X1 and X3. Data set D2, we fit Y on only X2 and X4. X3, we fit Y on just X1 and X4. And this is a strange idea because we have 4 predictors, but if we do this, we have more variation in trees, and that makes final surface more stable. I cannot really explain it well, but that is the fact, empirical fact. So because we have variation in the model, basically it's robust. It sounds strange, but that is the random forest. And boosting, the gradually determine the tree. So when we have, so the like the 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, and 0, 0, 0, 0, 0. Okay, so then the split is probably here, but we are not 100% sure. So we don't fit this kind of, curve. We don't fit this, but we just gradually fit the curve. So maybe we have this, right? Then after that, we randomize the training set, and we do this again and again. So we just gradually determine the tree. Maybe the 2B, so the details are later. So it's similar to bugging, but slightly different because the boosting is more sequential methods. So we basically take the difference between the fitted curve and the original observations, then we do it. Maybe I explain it later why this is different from bugging. Yeah. Okay, so the detailed algorithm and the examples we discuss next time. Okay, so I will upload the midterm scores maybe tonight. Then, So that's it. And again, the Wednesday, we will decide the presentation dates. So just check if which dates that you are available for presentation. I think 19th and the 21st and May 1st, I think. Just a moment, please. Yeah. Yeah. So 19th, sorry. Syllabus. Yeah. Sorry. 19th and 21st. 21st. Sorry. 19th and 21st. 19th is on Wednesday. Yeah. So this is Wednesday, Monday. Yeah, I hope that all people are available on all dates, but sometimes you have some issues. Okay, great. Okay, so if you don't have questions, see you on Wednesday.